Okay, this is AP Chemistry, Unit 1, Chapter 1, and we're going to talk some more about symmetric conversions and the system international units and prefixes that we've talked about many times before. You'll see that there's some new ones added. We know kilo through milli. We use them several times. Kids hate decimals. Decimals create money. But there's some added that giga and mega are even bigger than the kilo, and micro and nano are even smaller than milli. So those have been added. There might be some that you're unfamiliar with. But we need to be able to convert from one prefix to another. And you know we use our picket fences, dimensional analysis, to do that. You should be used to that by now. The metric system is actually used by every country in the world except for three. There's us, there's Liberia, and then there's Myanmar. Those are the only three countries left in the world that don't use the metric system. And here's some of the metric system units: kilogram for mass, the meter for length, the second for time. Kelvin is a unit of temperature. Degrees Celsius is also a metric unit of temperature. Ampere deals with electricity, and of course we know about the mole. We have also talked about accuracy and precision before, and accuracy is how close your measurement is to the actual value. Okay? We want to be as close as we can to the actual value. The closer you are, the more accurate you are. If you're dealing with a bullseye, a target is basically how close are you to that bullseye. That's how accurate you are. And then for precision, this refers to the degree of agreement among several elements of the same quantity. In other words, how close, if you take several measurements and they're all of the same, you're measuring all different types, or you're taking several measurements of the same thing, how close are all those measurements to each other? That's precision. That's how precise you are. And of course, both accuracy and precision depend on the instrument that you're using, and it could be a little user error involved as well. But accuracy, remember, is how close you are to a given value. Precision is taking several measurements and how close they are to each other. And in lab, we try to be as accurate and as precise as we can. Okay, that's just some more review from last year. We talked about sig figs all year long. This is just another review. We know that any number that's not a zero is always significant. Leading zeros that come before a number, such as this, those are called leading zeros. They're never significant. Captive zeros, like this, where they're in between two non-zeros, those are always significant. And trailing zero, when we say sometimes, that means only if you see a decimal. If there's a decimal in that number, then those zeros are significant. If there's no decimal, like in the number 1,200, you don't see a decimal, those zeros are not significant. If it was written like this, 1.200, then yes, those zeros would be significant. Okay? Now this is how we learned last year. And then here's just a simpler way of putting that. This is just summarizing a little bit. If it has a decimal, you actually see the decimal, then if you scan that number from left to right, then you're going to look at the first non-zero. That is significant, and everything after. All those would be significant figures. Okay, scanning from left to right, the first non-zero you come to and everything after. In the case of the number we had just a minute ago up above, we scan from left to right, we get to the first non-zero number, and we say that's significant along with everything after. 1, 2, 3. I would have 3 significant figures. That is if you see a decimal. If there's no decimal point, then we're going to scan that number. Instead of left to right, we're going to go from right to left. And we're going to start counting. I'm going to put start counting once again. at the first non-zero and everything after. Those would be significant figures. In other words, we don't see a decimal in this number, so I'm going to scan from right to left this time. I'm going this way. And so the first non-zero number and everything after would be significant. So here I would have 1, 2. I would have 2 significant figures. Okay? That is the same thing we said last year. It's just another way to look at it. This might help some people and it might not. That's just a new way to look at it. Okay? Nothing, I haven't said anything new yet. All this is just some review from last year. This is Chapter 1, the first part of Unit 1. Okay? All right, so the next little section talks about exact numbers. And exact numbers are basically anything you're going to use in your conversion factors when you're doing dimensional analysis. These have, we don't count significant figures in these when we're doing our calculations because these are said to have an infinite number of significant figures. Okay? So we don't count those when we're doing our calculations. These are not counted. And this is things like 1 inch equals 2.54 centimeters. That becomes one of our conversion factors, right? And that's not, these are not counted in our significant figure calculations, okay? Or 1 liter is equal to 1,000 milliliters. Same thing. That does not count in significant figure calculations. All right, and so what's the rules that for when we multiply and divide and when we add and subtract? And I put a star here because in chemistry, 99.9% of the time we're dealing with multiplying and dividing. That's dimensional analysis. We're multiplying and dividing, okay? And in this case, the number of sig figs, remember, is equal to your least precise measurement. We know that. Remember, the whole purpose of significant figures is we can't lie. You can't say in your answer that your answer is more precise than your measurements. So we have to go with our least precise measurement in our answer. Okay? And add and subtract, nobody ever remembers the rules for add and subtract, and we don't use them much. But the number of sig figs when you add and subtract equals the least number of decimal places. So we don't look at the whole number, we look at the number of decimal places, and our number should reflect the least number of decimal places. So, for example, if I have, let's say 6.8 plus 11.934, okay? And my answer I get in the calculator says 22.4896. Well, that's way too precise because my least precise measurement is just one place past the decimal. So my answer would actually be 22.5. You can't be any more precise than your least precise measurement. But remember, most of the time we're just worried about multiplying and dividing. Okay? So we use this when we do dimensional analysis, which is our picket fences that we love. Show your love. You know you love them. We've got to show your work. On the AP exam, let's say you're doing a dimensional analysis problem that's worth 10 points. Well, 1 point is for your answer, getting your answer correct. The other 9 points are your work, showing your work. So that's why I've always required you to show your work for your dimensional analysis problems. So this is just a little practice. If we know that 1 inch equals 2.54 centimeters, and remember that's an exact number, and we can calculate how many feet are in 240 centimeters. Remember, you start with what you're given in the problem, and we want to get rid of centimeters, so I'm going to say 1 inch is 2.54 centimeters, and then I need to get rid of inches because I want to know how many feet, so I'm going to say 12 inches, so I can get rid of that, and 1 foot. Okay? And when I calculate this, I believe in the calculator I get something along these lines. But we know that's way too precise. I only have 4 significant figures in my measurement, so my answer can only have 4. Remember, you look at the whole number. So this is my final answer. And like I said, on the AP exam, this would be worth 1 point. This would be worth 9. So it's super important that you show your work. Okay? Temperature is also in Chapter 1 in the book. The Celsius scale and Kelvin are the two that we're going to use. Never Fahrenheit. Even though we're in the United States, remember we're one of only 3 countries that still uses Fahrenheit, but we're going to be talking about Celsius and Kelvin. And then a lot of our formulas will require our temperature to be in Kelvin. And that's a simple, you don't have to do a picket fence to convert from Celsius to Kelvin. All you do is add 273 to your Celsius temperature, and we did that for the warm-up yesterday. Add 273 to your Celsius temperature, and that'll give you your Kelvin. Okay? That's easy. Temperature is easy. All right, density, that's a physical property. We talked about intensive properties last year. We did not talk about this word intrinsic, but density is an intrinsic property, which simply means it is unique to each substance. Water has a density of 1.0 grams per centimeter cubed, or grams per milliliter. That is unique to water. No other substance has that density, so that is an intrinsic property. It's unique to that substance. Intensive means the amount of it doesn't matter. It doesn't matter if I've got a gallon of water or if I've got a drop of water. That density is going to be 1.0 grams per milliliter. It's not going to change. The amount of it does not matter. It is amount independent, okay? The amount does not matter. All right, and the formula for density is mass over volume. The units are usually grams per centimeter cubed, and that's usually for a solid because you have length times width times height, right, to get your centimeters cubed. If it's a liquid, it's usually grams per milliliter. And we need to remember for conversion purposes that a centimeter cubed and a milliliter is the same thing. And sometimes you'll see, if you're going into the medical field, you might see 26 cc. That is the same as cubic centimeter or milliliter. It stands for cubic centimeter. So if you hear the patient needs 1.2 cc's of some substance, then that just means milliliter or cubic centimeter, okay? All right, this next problem right here is a very, very challenging problem where I'm just showing you that density, the density of a substance, can be used to do many calculations in chemistry. If you know the density, then you can do many different things with it. But look at this problem. It says a 55-gallon drum weighs 75 pounds when empty. What will the total mass be when filled with ethanol? We know the density of ethanol, and we know that 1 gallon is 3.78 liters, and 1 pound is 454 grams. So we want to know, when you take this drum and you fill it with ethanol, what will be the total mass? Okay? Well, we can find the mass of the empty drum. We can say, we know it's a 75-pound drum, right? And I know I'm going to put 1 pound down here, and 1 pound is 454 grams. Okay? I can get the grams there. And when I calculate that, I got 3,450 grams. That's the mass of the drum. Now, when you're doing, you have several steps to a problem, don't ever round off to significant figures until you get to the end. Always keep your numbers the way they are until you get to the very end, and then you'll round off to significant figures. So we're not finished yet. All we know is the mass of the drum in grams right now. Now I need to figure out the mass of the ethanol that I'm going to put in there. Okay? Well, I know the density of ethanol. And I know, if I know the density and I know the volume, I can find the mass. Well, how am I going to get the volume of ethanol that's going to go in there? Well, the drum itself is 55 gallons. So how can I figure out how many milliliters that is? I can use these conversion factors. And I know that 1 gallon from right up here is 3.78 liters, but I need to get to milliliter, because a milliliter and a cubic centimeter are the same. So I know that 1 liter is 1,000 milliliters. And that got rid of gallons and liters, and I'm left with milliliters. And I get 207,900 milliliters, which is the same as 207,900 centimeters cubed, okay? That is the volume of ethanol that will fit in that drum. So now I can use this density, 0.789 grams per centimeter cubed, equals the mass, which is what I'm looking for, over the volume, which is 207,900 centimeters cubed, okay? And now I can find the mass. And when I do this algebraically and find the mass, I get 164,033.1 grams. That is the mass of the ethanol. So I'm going to add this to the mass of the drum to get the total mass. So it would be the mass of the ethanol plus the mass of the drum, the empty drum, equals, hang on, equals the total mass, which I'm going to round off to 198,000 grams. Okay, this is a good multi-step problem that you'll see. This is a good AP chemistry problem. And I'm just showing you that you can use the density to find different things. Okay? All right, and then towards the end of chapter 1, we talk about what is matter, and we talked about this last year. This is very easy. We know matter is anything occupying space and has mass. Even gas, okay? Our three states are our solid, liquid, and gas. And we know that the solid, this is all you need to know for right now, has a fixed shape and volume. Liquid has a fixed volume, but it takes the shape of whatever container it's in. So it doesn't have a fixed shape, depends on what's holding it. And a gas has neither fixed shape or fixed volume. No fixed volume. It takes the volume of its container and the shape of its container. Okay, that's all you need to know for right now. All right, we talked about mixtures. They've been physically combined. A homogeneous mixture is the same thing as a solution. And this means that it's uniform throughout. It's smooth. You're not going to see any pieces. It's the same, like vinegar. Okay? Heterogeneous is not uniform. Okay? It's not the same throughout. You're going to see pieces, like ranch dressing, okay, or any kind of salad dressing. Good rule of thumb is to pretend like you've got a great big container full of whatever you're talking about. If you're trying to decide if it's homogeneous or heterogeneous, you've got a big container of it. If you split it up into several different, poured it in a cup for 20 different people, is every person going to have the exact same molecules in the exact same amounts in their cup? If the answer is yes, then it's a solution. If it's no, it's heterogeneous. Okay? And we can separate those mixtures. There's 4 different basic processes. There's more than that, but these are the main 4. Chromatography is how we separate dyes or inks. Okay? Filtration is based on particle size. We can use filter paper to filter out. The liquid would pour through the filter paper and then it would catch the other debris. So it's based on particle size. Distillation is how we separate liquids based on boiling points. And I told the story in class about the cherry Coke and how we boiled it and let this solution collect that looked clear. It looked like water, but when we smelled it, it was actually the cherry extract. We were separating that liquid based on the different boiling points. And this fractional distillation, even though that sounds complicated, all it really is, for example, if we have salt water, how would we get the water? How would we get the salt out of it? We would evaporate, okay, and be left with the solid, with the crystal, okay? That's all that is, if you're trying to separate a liquid from the solid, okay? This is physical. Compounds and elements are chemical combinations, okay? They're chemically bonded. Compounds have a constant composition, that can only be broken down chemically. Like H2O or CO2. We can break that down chemically into its elements. But the element now cannot be broken down into simpler substances, except for atoms, right? We know that atoms, that an element is made up of atoms that are all the same, okay? So it can't be broken down any further chemically. This is simple as it can be unless you're talking about an individual atom of that element, all right? And that is it for Chapter 1. We'll start on Chapter 2 tomorrow.